All right, guys. Yeah, so as Nathan said, I'm a principal engineer at Basho. I've been there for 4 years. And today I'm going to talk about something that has not really anything to do with Riak, just Erlang data structures. Even then, this talk's actually a little bit misnomer. I came in hoping to talk a lot about lots of data structures. In the end, I ended up talking about one, and then talk about other stuff. This is more adventures in rewriting things as NIFs to make things fast, not just data structures. But bear with me, you'll see how it goes. All right, so as we all know, Erlang is a really highly productive and pretty awesome language. I mean, especially if you are familiar with it and get used to it. It's scalable, it's distributed, it's fault tolerant, it's really nice. But there's some performance envy with Erlang. Erlang is a great language to be able to build good, medium performance, highly scalable apps quickly, probably faster than any other language that I know of. The problem is if you're one of those few folks who gets into the situation where, oh wait, I need to be faster now. It's sometimes really hard. The standard library has data structures that aren't the fastest in the world. You get to cases where you run into lock contention in Beam. There's fun challenges there that a few people who've been with Erlang for 10, 15 years, you hit that eventually, and you're like, wow, that's kind of annoying. And so one thing that I really wanted to set out and do originally a few months back, actually a couple of years back now, when I first started some of this work, was to say, well, could we build new black boxes, these nice components that are highly performant, where we can still write most of our application in Erlang, but are benefiting from more efficient data structures, more efficient message dispatch systems, and things like that. I don't know, but as the talk will talk about some of the work that I've been trying to do in that space, and perhaps motivate other people to try to do some of it too. So the solution here was, hey, let's write a NIF. Of course, NIFs are scary. Use them with extreme caution, right? You've all seen this on the Erlang website probably. The funny part is before this warning never existed originally, and then it added later after it caused lots of problems. So NIFs caused the problem. And the thing here, the thing with NIFs though is you have to use them sometimes. I mean, in Basho, we use NIFs to interface with eLevelDB. We use NIFs for part of Bitcast. So most of the databases that are written in Erlang, for example, still have their backend written in C, because that's just the way the world works. And so we use it a lot for interfacing with things. But we really at Basho haven't ever used it for just high-performant, data structures, or for other little things like that. It's mostly just been for interfacing with existing C code. But we'll talk a little bit here of using it for different purposes. So there's actually 3 things I'm going to talk about today, as I mentioned. So data structures, yes. And then I'm also going to talk about message dispatch. So the challenge here of wanting to send messages to a worker pool of processes, have built-in overload protection, have built-in load balancing. And that's actually something that's really hard to do in pure Erlang efficiently. Trust me, I've tried. A lot of us have tried. And so here's an example here of trying to actually do it as a NIF. And then at the end, I'm going to talk about also stats collection or statistics systems. So basically computing mins, maxes, and histograms over events. Most of the libraries people might be familiar with in this space, like Folsom and Exameter, are pure Erlang ones, and they have performance problems. And so there's some prototype here too of building a statistics collection system as a NIF as well to fill in that space. So data structures. So we kind of know the big standards here in the standard library. We've got ORDICs, DICs, and GB trees, and we actually have maps too. Although maps were slow for large sets of data until apparently yesterday. So R18, came out yesterday, and unfortunately, I didn't find any time to go and benchmark the new maps. I really wanted to update these slides, but I didn't. But maybe maps are totally awesome now, and this whole rest of this talk doesn't need to happen. But in any case, we're going to stick with what we already do have. Since I also imagine most of us aren't running R18 in production right now either. One day late. And so if you were to go and just run a very simple benchmark, and this is a forward insertion benchmark. So just you're inserting keys 1 through the top number here. In a fold, into a set. So it's a forward insert. Interestingly, you'll get completely different performance results if you insert the keys in reverse order and so forth. But and so forward insert here, we can, as we all know, we know ORDIC. And the numbers here are in milliseconds. So we know that ORDIC gets terrible when your key set gets large, right? I mean, after 10,000 keys, don't bother. Heck, after 1,000 keys, don't bother. DIC is pretty good. It actually scales more or less constant with your rate, and then it gets really strange at about 100 million. It starts being not so great anymore. There's a pretty big jump here. And then GB trees, while are slower than DICs, they're actually not so bad here, but they're slower than DICs if you look at fetching. So fetching is not on these slides, but fetching is something DIC is much better at. And that's why most of the time you don't use GB trees, we use DICs. But GB trees actually scale very well for this insertion case here, even up to the million nodes. Now granted, that's also because we're inserting them in forward sorted order. If you were to invert this in reverse order, GB trees do actually much worse. But And I actually have all those other numbers, although I think I forgot to put them in the slide deck. But I can bring them up during questions if anyone cares about forward and backwards and random insertion and all that other jazz. I have all that. OK, this is interesting. And here's the real answer. There is no way you're ever going to store more than 10 million items in any Erlang data structure on the heap today. You can't. I mean, even Dick, this takes more than 10 minutes when I tried. So yeah, good luck with that. What I'm going to talk about in this talk, in mode of an example, is going to be this new B tree structure, which if you notice here is actually not any faster than a GB tree. It's about the same because, well, it's a tree data structure, and so it should perform about the same as a GB tree. The reason why we're going to talk about it is this is the version here for the pure Erlang version, which is about 269 lines of code, and it's a good place to start. And then this gets rewritten as a NIF progressively and gets faster as we do that. And again, as you expect, it's about the same as a GB tree. We'll actually get and talk about what that data structure is in a few slides. All right, so what's one of the things that's really cool about functional data structures? And this is true for Erlang, it's true for Haskell, it's true for OCaml, is that they're immutable, right? They're immutable data structures. It looks like you're getting kind of these copy and write semantics, but you have efficient term sharing going on beneath, so the structure's shared and things are nice and fast. So, standard, you build a dict, you store some number in it twice. Even though we stored them twice, these look like they're copies, right? So if I read from dict 1, I get 10. If I read from dict 3, I get 15. We don't update it. Go do this in C with maps or something, and it would update. It's a copy. It's an in-place update. So this is really cool, and the Erlang VM and Haskell and all the functional languages that do this actually do this pretty well, and it's nice. And that's a really cool property because I don't know anyone who's been an Erlang programmer for years. You take advantage of this property a lot. There's lots of algorithms that are much easier to write when you're just doing copy and write and mutable updates, and you kind of that's second nature. You get used to that. But one of the things though is for performance cases, a lot of times we end up using ets in our code base, which is fast. Here's ets, the same benchmark. Wow, it is really fast. This is actually the ordered set ets to be comparable with the GB tree. So hash set ets is actually even faster. About another half of this for this particular benchmark. And it's the first that actually can get to 10 million. Yeah, it takes about 5 seconds, but it can get there. These guys can't. And that's neat, but here's the problem with ets, right? You lose the immutability property. There's no ets snapshot, right? There's no way to update an ets table and have it efficiently give you a snapshot view of that. Although ets has some benefits. A, it's fast, like we just saw, and B, it's concurrent. So you can actually update ets from different processes. You can read between them. That's really cool. You can't really do that with, a dict, right? It's copy and write. And the data is stored off heap, which can be good or bad, right? In some ways, it's great because it reduces the garbage collection pressure on a process, normally. Although it's bad because every time you access it, you're then having to copy the data into it or out of it, off to the off process heap. But usually that's fine. If you have a really large data structure that is 10 million keys, you're probably only ever accessing a fraction of them at a certain period of time, and so that's why ets generally works out well for us. So what I want to do here is say, okay, could we do something that looks kind of like all of the above? So something that has a mutable structure, so you can snapshot it. You can treat it like we treat dict and ordicts. But it also has shared structure, but it also can be used off heap. It's also faster, and so forth, and you can use it concurrently between processes. So that was, the first thing here. And so, okay, let's go and build a copy and write B tree, a cow B tree. And so this is fairly simple. It's a B tree that is not really implemented as you normally implement as a tree. Think of this as just levels of sorted ordicts. And this is, pretty straightforward. So you initially start out with a root, which just has this is an ordict. It's tuples. I'm storing the value 1, 10, 5, 50, and 9, 90. So the left value here is the key. The right is the value, standard tuple in an ordict. And let's assume here that this is a B tree that only has up to 3 elements per block. So I guess it's a 2-3 tree effectively. That's only because it fits on the slides. In practice, you'd want to use much wider B trees here, up to probably 64 to 128 elements. But OK. And so we have the value here, and let's say we're going to go ahead and insert the value 3, I believe. Is it 3 I insert? Yeah, it's going to be 3. So we're going to insert 3 here. Notice when we insert 3 into here, it would violate the size property, right? It's going to go from 3 elements to 4 elements. 4 is too big, so you're going to split it. And so we're going to split it here into 2 chunks, the right half and the left, or the left and the right half here, as you'd expect. So 1 and 2 go to one brand new ordict, and the other side goes to another ordict over here. We now have a new root, which is now referencing these guys. So blue are inner nodes, yellow are leaf nodes. So it's like a B plus tree kind of. Again, these are references. This is just me trying to show an Erlang term structure broken out. In practice, these are nested, as you'll see in a few slides. And then, OK, we insert the 3. After we do the splitting, there goes the 3. OK, as you'd expect. Again, it's an OR dict. OK, now let's go ahead and insert another number. Let's insert a 6. And since there was already space here, we just put it straight there. Again, it's just an OR dict update. All right, let's go and insert some more numbers. Again, now we're inserting a number we're inserting 4. 4 would have caused these things to split. So we would split and then insert the value there. And again, we would now update the top root again. Now, the interesting part here is the root now is actually full. So the next split's going to split the root, and the tree is going to increase in height yet again. So we do that where we inserted, what we insert this time, a 6 or a 7? I should have actually, yeah, it's a 7. So inserted the 7 here, which caused this thing to split into 5 and 6, and then the 7 and 9. And you kind of get that. And this is conceptually how GB trees work too, just a slightly different approach. And if you notice, so this is just layers and layers of OR dicts. Pretty straightforward to reason about. Now, this graphical representation is kind of strange. There's this, and you have to look up this. In practice, this, though, in Erlang is just a nested data structure, which internally has references, right? And it looks like this. I mean, this is that entire tree right there, nicely pretty printed on the prompt. It's just a OR dicts of OR dicts, where the OR dicts in the very bottom are special versus the OR dicts that are on the outside. So what's the actual state if you were to build this B tree? So I think I only put the lookup code here. The store code's not too hard either. The splitting code's not too hard, and the erasure code isn't too bad either. The whole thing is 269 lines of code, but this one's the only one that fits on a slide to easily talk about. So the deal here actually is this tree is just this data structure we talked about, and one other component. It's a number. It's the height. And so that's just when you're recursing down the tree, you know if you're at the leaf or not yet, just by knowing if you're at the height yet. So you start at root 0 and you increment down. And so for that, we don't have to have different tuples and pattern match on if you're a leaf or not a leaf, because if you do that, it's slower. So having the bare unlabeled values with just the root works fine. So OK, find is pretty easy, right? You start up, you just pull out the height, you start at 1, and you just recurse down the tree. If you're at the height, then you know you're at the leaf node, and just do a regular OR dict lookup. And if you're not, then you know you're at an inner node, which is still an OR dict lookup, but it's slightly different here because we want to actually find sort of the value and where you are. So this search is not quite, so it's not an OR dict, it's a lower bound lookup. So it's where you are, it's not an exact match, it's the place that you are that you would fit in sorted order that's not higher than you. And so you get that and you recurse down. But that's the lookup mechanism for this. The store mechanism is basically the same thing, except there's the ability to look at overflow and splitting, and then when you split, you can increase the root height. And erasing is similar as well. That code I'll put up online for anyone who cares about for that. But anyway, if we were to implement that and run it, it's, again, the performance numbers we've shown earlier, which, again, is about the same as a GB tree, although this is much simpler than a GB tree implementation. I'm not saying it's better. The reason I care about it being simpler is because I'm going to go rewrite this in C. And I don't want to write GB trees in C. Whereas this nice, simple OR dicts of OR dicts is pretty easy to go and build. Well, you'd think. It actually gets hard. So this is what we want again, though. We don't want a pure Erlang thing. We want something which is, a concurrent, off-heap, awesome data structure that's a NIF. OK, so we're going to write a NIF to do that. And once you go into C, it becomes a challenge because, oh, wait, OK, now we have to deal with the fact that we need copy and write semantics, so we need to copy stuff. OK, if you copy stuff, where are you just doing a malloc or a new, depending on your language, or a no? If you do that every time you copy something, the allocator is going to kill you. So you have to be smarter now and do some kind of slab allocation or bulk allocation. So you have to do that. That's not too particularly challenging. These are all fixed size dicts of a certain size, so you can just use a fixed memory pool slab. It's easy. Hard part's the snapshots. How do you snapshot? How do you do this copy and write semantic and do efficient snapshotting in a concurrent setting? The hard part isn't the snapshot, really. That's actually kind of easy. The hard part is how do you clean up the snapshots when people aren't snapshotting them anymore? How do you free the data? And for anyone who's familiar with lock-free data structure work out there in the literature, this basically is what's known as safe memory reclamation. It's a thing we get for free in a garbage collection language like Erlang, or the folks in Java get. When you don't have a garbage collector, and so you never know when it's safe to actually delete something. If you just remove it from your root from your tree, and then delete it, there could be a snapshot that actually still has that root in it. Oh, wait, there's a problem. And then, of course, just dealing with atomics and ordering. That's just tedious, but it's not super hard. You just have to know what you're doing and take care and deal with the million seg faults you run into along the way, and then eventually it works. But the interesting part about the safe reclamation here is that most of the time in something like C, right, you're going to use safe, like C++ today. Most people are just going to use like a smart pointer, right? A nice reference counted pointer, and that's great. The problem is for a giant tree structure, when a smart pointer would be kind of annoying, because if you wanted to copy the tree, you don't just copy the root. You now then have to go and copy all of the pointers, or at least not copy them, but have to increment the reference counts on everything it touches. Which if you have a really large billion element tree, which has maybe 10,000 actual nodes that represent that, that's 10,000 reference counts you got to update. And yeah, you can do things like proxy objects to try to reduce it, but still there's a lot of bookkeeping you need to do there. And so that's not the approach we want to do. Instead, we want to look at is other types of safe memory reclamation, of which there's a few out there. People might be familiar with hazard pointers, epoch reclamation, pass the buck. There's various ones out there you can go read about. We're going to go with epoch reclamation. So epoch reclamation, which I'll explain in this talk, is what we end up using here, although we extend it a little bit. So the idea behind epoch reclamation, it's a grace period detection system, SMR system. It's similar to RCU. So RCU mechanisms like in librcu or liburcu, whatever it's called, are another form of grace detection as well, but implemented in a different way. Epoch reclamation is actually very simple. The idea here is basically like if I have 3 threads here, and they're reading concurrently, and threads 2 and 1 here started reading this data that's actually being deleted by this writer right now. But since it was deleted while they were reading it, they actually still have pointers to this data. Like, if this was, say, the root of your tree, they still have that root and they're still traversing that root. So even though you've logically deleted it now, you can't actually free the data yet. At some point in time, this guy's going to call this the synchronize. That's the basic primitive of epoch reclamation here, or any of these grace period systems, where you say synchronize, and after the synchronization is done, this basically blocks until it's safe for you to free anything. You've detected a grace period of which anything that could be deleted before you call it synchronize can no longer be used by anyone afterwards. And so that kind of makes sense here. Whenever this snapshot ends and this snapshot ends, that's when this ends. So it's the longest running snapshot there. Again, there's different ways this can be implemented. The way this is implemented in epoch reclamation is based on this notion of epochs. So there's a global epoch that you have, and then when any of these threads goes and modifies the data structure, they basically copy that. So they copy the global epoch, they have their own version of it, and every thread that can modify this data structure is known. So there's a list of all of them, and they're copying it to their own version of that. So if there's 5 threads, you have a little slot of 5 slots, of which each of those threads, when they go into doing this, copy the global epoch into their slot. And what happens here is they just do that, they copy it, they do what they're normally doing, and then when they're done, and then when they re-enter the region in the future again, they would copy it again. What happens here is the writer, the guy who does the logical delete here, when he calls synchronize here, what synchronize says is that's where the smarts are. What synchronize does is it's going to block until it is seen that all of the possible readers are either not active, so they're not in a region at all, or they're in a region where they have the epoch that matches the global epoch. So they're at the current value. If they're at the current epoch, then what the synchronize does is it increments the epoch by 1, and then it once again rechecks until everyone hits that epoch again to increment it yet again. The requirement here in epoch reclamation is you have to increment it twice before it's safe. Because there's epoch that people were in before that was unsafe, and then there's also the epoch they entered into when you were starting synchronization that's still unsafe. But it turns out 2 is enough. After 2, you're fine. And there's a research thesis in the UK that actually proves this. So 2 is all you need. But the deal here is you go in here, and you can kind of see it here, right? This guy still has a reference to this object. He did here as well. He still does lead into here, but this 1 still does here. While this 1 doesn't have a reference to this object, this 1 does. And so 1 is still not safe because he could still have a copy there. But once they've both transitioned to 2, at this point in time, there's no way they could have referenced this value that was logically deleted back here. And so yes, it is clearly safe to delete it over here. OK. And the way epoch reclamation normally looks, and so for epoch reclamation here, I actually use implementation as in concurrency kit. So concurrency kit's a well-known C library that's out there. And the primitive, though, basically looks something like this. So it looks kind of like a critical section when you're about to go, and so a reader does a begin and an end, kind of like you would lock and unlock around a region. This is where you're copying the epoch into it. Here's where you're saying you're no longer active. Synchronize. Here's the synchronize I just talked about. Sorry. And so, begin, end, they do some stuff, whatever, this runs forever. The writer comes in here, he deletes the old root here, so he updates it to copy and write. He does some switch here to the new root, there's some atomic, swap here. The problem is that, he can't delete this yet because someone over here could have accessed it while he was updating it. But he does synchronize. After the synchronize is done, it's safe to delete it. You can delete it here now. Woohoo. And it turns out you also don't need to do synchronization blocking. This can also be just polling. So every time you come through here, you check to see, can I do it yet? Oh, it's not safe yet. OK. Oh, it is safe? OK, well, then go and delete some stuff. And so you can accumulate a garbage list and just throw it away whenever it's safe. But the blocking is the simplest one to just conceptually explain. All right, the problem with epoch reclamation is this only works for short-lived readers. It only works in a case where I'm going to come in, do something, and then immediately leave. Because this guy, synchronized, he's going to block. So basically, the writer can't block readers. But readers can block the writer indefinitely. So the longer you have a reader who's reading into a snapshot window, the writer just forever stalls. And so this makes sense for a copy and write structure where it's like, go in, give me the current pointer, and leave. Not a persistent snapshot like you would have an immutable, I have dict version 1, dict version 2, and dict version 3 that are on my heap, and I'm using them however I want to use them. Those are long-lived snapshots. Those aren't what you want to use here. And so that's generally the problem with epoch reclamation is this. But we can solve that by extending epoch reclamation a little bit to also have a notion of a separate snapshot concept. So we take this and we extend it a little bit to look something like this. So in addition to there being for every node, every reader, a slot where they're copying their epoch, the current global epoch, there's also this notion of where they have a snapshot slot. And in a dynamic system like Erlang, where you're doing NIFs, every time you create a new snapshot, it actually creates a brand new snapshot slot. But in this example here, we assume there's some fixed number of readers that have some fixed snapshot set. And the difference here, the only difference here is he begins, he gets the root, he calls this snapshot first, and he ends. This snapshot here is we've introduced this new thing called the global epoch over here. Probably should call it a generation instead of an epoch, but since I'm using the word epoch twice now. But basically, every time the writer moves along to a new phase, he has a new generation. This is kind of like a vector clock would be in a distributed database, or frontier, a dot. And the idea here is that all the objects that you allocate are now also have a birth date and a death date. So the birth date is when they are allocated. So when they're allocated, they get the birth of the epoch that they were created at from the writer. And whenever the writer ends up deleting them logically, they get the death date at the time that they were deleted. And these are just pushed into some garbage list that gets collected at some point down the road. Otherwise, so basically the same thing, right? Same logic here, except I'm adding birth dates and death dates now. And I'm incrementing this epoch here. So what's the collect look like? Well, the collect still has the epoch synchronized. We still need that. That's to know that we've moved to past when the last. So the death date is associated with the root still. So that root is still generated at a point in time. We still have to wait those 2 SMR epochs before we can actually trust that death date, where that death date tells us that no one can have anything before that death date. So we still need that. So that's why we have to synchronize. But after that, though, we can then garbage collect anything that is no longer live. Live meaning that it is not there's no snapshot that contains an overlapping set from that guy's birth to his death. So pretty straightforward. You go through all of your list of your snapshots. Again, this is a list of everyone who's a reader. You know who they are. And you look at the epoch that's listed in there, and you say, OK, if this epoch is for every item in the garbage list, if someone has an epoch which is greater than or equal to my birth and less than my death, then they can still see me, right? They're in still my lifetime. And so that value must live. But if no one does, that value can die. And then you just push these into our little local state here. And down at the end, if he lives still, we keep him. If he's not, we throw him away. And again, delete could be whatever we actually do here. And then at the end, we just keep around the ones that we keep. And in the future, new garbage collection will deal with that. And so whenever a snapshot goes away, eventually you will garbage collect everything you can. The nice thing about this is that if you don't have any snapshots, you're going to be garbage collected immediately. Because the writer is always at a certain point in time. There's no snapshots. The second he calls epoch synchronize and calls collect, he's going to free stuff. So you're not accumulating garbage in the front. Likewise, if you do have a snapshot in the past, yes, you're going to keep old stuff alive. But all the new allocated objects in the future that you create, those are going to be thrown away if you rewrite them. So anything that's newer than that snapshot will also get cleaned up quickly as well. Unlike regular epoch reclamation, whereas in regular epoch reclamation, that's all you were using, you can't clean up even the new stuff until everyone just moved on to the new epoch. And so that's one of the things that's nice here, is that we're keeping this epoch short, this begin-end, but this snapshot object we created here, this thing can live indefinitely. That can live for however long we want to live on, and that's what we can pass up to Erlang as our Erlang resource or whatever that we're going to use. OK. So this is a lot of C code. I'm not Erlang factor. I want to talk about C code because this is the hard stuff, right? So this is all the stuff you have to get to then say, OK, now I can write a NIF that has immutable components and safe memory reclamation. So now let's go ahead and start doing that. Oh, wait, there's one more thing I have to talk about. And so here's the thing. That's all about reading. The problem is writing is also a challenge, right? So there are really fancy concurrent data structures you can build that allow you to do multiple writers. B-trees are a very hard one to do that way. They do exist, but it's a very complicated algorithm to do concurrent B-trees. And even then, there's still locks. There's just multiple locks. It's finely sharded locks, and you have just a bunch of different locks. And so you're still locking. You're just locking in different paths. But paths that don't overlap aren't locking. So one thing we could do is we could just still have a lock around a single writer and do a single writer B-tree, which sure, that's what the Erlang code was, and that is my additional implementation. Or you can optimize it a little bit and use this technique called flat combining, which is another technique that is used to sort of optimize it. It still has a single lock, but it works out better in practice. It's this weird thing where if you read rich paper, it's like, yeah, this should be unsurprising, but in practice it works out better just because of the way the processes are designed. It's because you have less cache contention, you have less fighting over the structures. So what flat combining basically means is that when you have multiple people who want to update a data structure, and instead of having them all wait on a lock, where one guy gets a lock, does his one update, leaves, the next guy gets a lock, does his one update and leaves, and the next guy does it, you do a case where you try to actually coalesce it, where the first guy who gets a lock actually does the work for everyone, or everyone within a certain time bound. And so he gets a lock, does a bunch of work real quick, which it's all in his cache, you can do updates really quickly, and then he goes away, and you're not ping-ponging this lock back and forth. And there's a few aspects to epoch reclamation. The main thing here, though, is that each actor or thread, they have their own little state here. That's thread local. That is where they put their little request. For a B-tree update, it would be write this value or delete this value. Those are the two writing type of operations you can do. And you would go and store it in the request field. And then you're going to spin on this ready field. So you're going to do a spin wait, potentially, on this ready field. The difference here is it's not a single lock. It's a single in your cache field. So if someone else is, no one else is going to be ping-ponging on that. And so everyone has their own separate one here. And again, I'm talking spin weights in practice in Erlang. You don't use spin weights here, but and I'll talk about that in a second. But it would happen, and then someone's going to get the lock. So we'll just kind of illustrate this. So one guy comes in here. He wants to do the update. He puts a value in the request field here. He also says, is a structure currently locked? It's not currently locked. So he actually becomes the right combiner now. So he actually locks it, and he starts doing the work. While it's happening, someone else concurrently comes in here. He sees that it's already locked, though. So he puts his request here and just busy waits on his ready field here. Same thing with this other guy. He puts a request there and busy waits. This guy over here, while he's running, he's going to do his request. Then he's going to notice, oh, wait, this request is here. He's going to do that guy's request and set the ready flag true. And then he's going to notice this guy has a request too, and he's going to do that as well. And so this one scheduler thread is going to do the work for all these guys, or this one, whatever, not this one thread. And then when he's done, he'll be done. These guys will come off their ready here. They'll be done, and everyone will move on in life. And then you're faster because of the fact that you did the right combining. Now in practice, how this actually implemented in my code for Erlang is there is a brief busy wait here, but there's a lot more metadata where after busy wait, the scheduler, the NIF actually sets something up where we get a message instead when it's ready, and it returns back to Erlang so that you don't block the scheduler thread forever. And of course, if I was using R17 or newer, there's actually built-in support now in the NIF API to actually do a suspend from the NIF, just like the BIFs can do, where you can break out of it, which I could do as well. But this was implemented in R16 originally, so responding back works. But effectively the same thing. You come in here and you spend a brief period of time on that, and then you're not. You just run back in Erlang, and eventually they'll ping you when the right combining is done. OK. So all that background of how we have to handle this to make this actually work the way we want to without a garbage collector. Now let's actually talk about how it looks like. So once you build this, you have something that looks like a dict. But this is actually a NIF with term sharing behind the scenes. This is concurrent off-heap data. So you create a new one, you store value, you store a different value, and you get 10 and 15 just like you would with a dict, which would not be true for ets. And then these two copies here are very, if this was a 1,000,000 element tree here, and you updated this, you literally would have only one value different between these. Well, one path. The root would be different, and whatever values you had to copy down from the root down, but that's it. Everything else would be eternally shared. So this is really cool. So how does this perform, though? Well, it's faster than the B-tree code before, the non-NIF. Yay. It's still slower than ets. But it actually is faster than any, since we know that this was basically as fast as the GB trees, which was faster than dict for the larger sets, we therefore know that this being fastest, this is still faster than any of the on-heap in Erlang structures. Outside of maps, because I didn't test maps in R18, maps in R17 were terrible for this, for 1,000,000 keys, so maybe they're faster. But we get some decent performance here. We are slower than ets, though, because we're copying stuff. Ets is doing in-place updates. It's not doing copy and write. And so we're slower here, but we do have the benefit here that we are snapshots, right? We do have immutable properties now. So we did what we wanted to do. We have an immutable data structure now that is almost as fast as ets. Great. Too bad we couldn't get there, but I think with some more optimization we can. I think we can get there. The interesting part is this actually is slow for reasons that are a little silly. This is slow partially because in Erlang, every time we create each one of these is actually a new ets resource. So ets resources NIF resource. And so there's a notion in NIF where it's basically a garbage collector resource where whenever the Erlang garbage collector collects that term, that'll eventually call a destructor over in the NIF land, which then does it. And so each of these are actually snapshots. Like back in our old case here, we were talking about snapshots here. Like these long-lived entities that prevent data from being reclaimed, the thing you need to scan over in this giant list here each time. those are every one of these references that you see over here. Well, unfortunately, if I have a loop that's just a recursive loop that comes in, has an accumulator, adds a value to it, and recurses, standard tail recursive loop you do in Erlang to fill something up, you don't immediately garbage collect after you recurse. You just keep filling up a bunch, and eventually you garbage collect at some point in the future whenever your minor collection or whatever gets triggered. And so if you actually profile it, you end up seeing that we'll get to a case where we'll have like 200 snapshots that are not even there, but we have to scan over them and keep data alive because of them. And then eventually Erlang clears them all, and then the garbage collection round frees them all. And as you add more and more of your data, and your data gets larger, and your process gets larger, you have larger and larger of these snapshots that stay live before they're collected. And so unfortunately, the Erlang garbage collector is actually what makes this harder for us, because we're keeping all these snapshots around. And normally, when you think of, I'm going to build a concurrent data structure, you don't think, and I'm going to have 500 snapshots of it live at once. You generally have maybe 10 in your application logic, but because the way the garbage collector works here, every one of these ephemeral temporary copies stays alive for quite a while. So that's one of the performance challenges we have. OK, so let's say we not have the immutable property yet. Then let's get rid of the immutable stuff and actually say, OK, I like ets. Let me just make something that looks like ets. So this is now the M version of this B-tree NIF. So we have a name table, basically. Give me a name. And we just insert into that name. And these just come back as OK. You're not getting a mutable thing. This is kind of like ets. It's mutable state somewhere. And just like ets, it is a mutable state. So you can read it in another process just fine over this value. It is ordered, though. Unlike ets, though, you can actually still snapshot this. There is a btn_m snapshot, which does give you a snapshot then, which works like a regular. It works with the same API you have here. So you can fetch it, although you can't store to it anymore, but you can fetch from it. That's cool. So it is that one nice feature. You can do snapshots of it. This looks kind of like ets, but it's still slower than ets. But it's faster than, it's getting much closer now. So before, we have the bottom NIF down here, which is still kind of terrible. This one's in striking distance. It's getting closer. It's still copying, that's why. At the end of the day, we're still doing copying. It's also ordered, it's also doing some extra work, and it's not as optimized as ets has been. So, I set out to try to make something that was faster and better and awesome, and well, okay, it's not faster. But it does have some interesting properties, and that's where we are. And I believe that is the end of the data structure part of this talk. All right, so moving on. So now we're going to look at a few other things. These are other NIF-related things here. That are more complicated than just like a low-level data structure. These are more like other primitives that would be useful to have in a high-concurrent system, a high-performance system. So one of these is a worker dispatcher, or at least I'm going to call it. This is a problem that probably most of us who use Erlang have. Heck, you even have this if you have supervisors, hot supervisors. The deal is you have a lot of processes that are all sending messages to a worker pool. And you want to efficiently send them to the message in the right worker pool. And you also want to perhaps have overload protection as well. So maybe you want to have, if I do have too much work where everyone's message queues are filling up, it'd be kind of nice to just discard some of these messages. So load balancing, overload protection, et cetera. In React, we actually have this, we have a thing we built a few years ago, actually I wrote a few years ago called SideJob, which tries to solve this problem. And it was mostly a work balance and select system, but it was also largely an overload protection problem. We dealt with it after a case where just people have clusters of a certain size, and suddenly someone, they get really popular, and their user base triples in a day, and there's really nothing you can do if you're queuing all that data in your vnode mail or your Erlang mailboxes. Erlang is going to get really sad really fast, and so you need to discard that data as soon as possible. So overload protection. So what SideJob does, and this was implemented many ways and rewritten in many ways and rewritten, but it's pure Erlang until it was fast, and I don't know if we can make it faster, maybe. But what we did then is this is using, there's a set of workers. So in this case, here's a 6. And each one of these workers has a counter associated with them. And these counters are stored in ets. And these counters are partitioned. So there's a different counter for each of these workers. And we use an atomic ets increment. And anyone who knows anything about ets and played ets magic, that's like the fastest way to use ets is atomic increments to partition counters. And hopefully get lucky that they don't map to the same sub-lock in ets. Most of the time they don't, and you're fine. And if you really care, you could actually control the names here, because we don't care about the names. But anyway, atomic partition counters. And what you do here, these are all representing message counts. So every time you're about to go send a message, you're going to increment the count. And then every time the guy gets the message, he's going to decrement the count before he actually does the work. Pretty straightforward, right? How does this work when you actually want to go send a message? So when you want to go send a message, again, we have lots of processes to go send this. So what we do is we actually shard into this table at a certain point. We jump into this table at a certain point. We hash into it based on your scheduler ID. That's the hack we do. So the hack is Erlang, you can do Erlang system info or one of those calls and say, give me my schedule ID, and you'll find, oh, I'm schedule ID 1 or 2 or 3. And so we say, OK, each schedule ID that's running concurrently will jump into the table at a different point. and they will try to send it to that guy first. And then if they can't send it to that guy, they will move to the next guy round robin, and since you're jumping at different points, you know you're going to have lower contention, right? Let's assume in this case here that the max count is 8, so after 8 we throw messages away. We tell you overloaded. So this guy over here, he tries to send a message. He sees the counter is still 5. He increments it to 6. Cool, he can send the message, and so he sends the message to this PID, whatever the sixth guy is. This dude over here is trying to send this guy. It's 8 though. It's full, so he moves on. That's 8. That's full too. He moves on. Oh wait, this guy's not full. He can increment. He sends it to that guy. Okay, it's a pretty straightforward design here. You know, and it actually works pretty well. I mean, you know, trivial to build, you performance test it, you do this stuff. There's some things you play around with. What's the right number of workers? How do you partition things? How do you build your keys? But you know, it works. It's still not the greatest thing in the world, right? If you think about this, that's a lot of work for what is kind of just increment some atomic counters and subtract some atomic counters. So we should probably just use a NIF for that, right? So we do. I'm not going to show the C code, but I'm going to show the API of this new NIF that we've built. This is called dispatcher. It kind of looks like an ETS table in some ways. You create a named dispatcher, so a resource, so in this case your test. And then you can have listeners who register to that. So I can say I'm going to listen as a test listener. Here's my PID. And then anyone who wants to send it just says, hey, give me a PID, one of the PIDs, valid PIDs. And internally it's doing the locking, the load balancing, and the overload. And this can fail. So actually this shouldn't be a fine. This should actually be a case here. But this actually can return, this actually returns error or overloaded if it's overloaded. And so this may fail, and then you're just supposed to throw the message away. But for the slides here, we assume it works. And so not too terribly challenging. Oh yeah, and when you get the message, you have to ACK it down here. Interestingly, it's not as fast as I thought. It's only about 1 times faster under contention. That's a lot of contention. Like you have to have, you know, like a 16-core larger box with the schedule threads and lots of processes running and doing it. So like on my laptop, it's like 40% faster rather than like 1.5x. So I don't know, probably more to look into there. I would have expected that would have been faster. But who knows? There's still more work to look into that. But that's one of the things that I think would be a very useful primitive as well. And if we can get this right and how they perform it, send messages to someone. As an aside, there was just in general using this just as a way to discard messages is useful. One thing we don't have in Erlang is bounded message queues, but this basically gives you a bounded message queue. I think we had a heated pull request a few months back that tried to add bounded message queues to Erlang, and that didn't happen. And again, it's hard to change the actual VM as is and not worry about breaking something. But having some external library, we just use something like this, which then, yes, behind the scenes, it does send a message. But before it sends those messages is throwing things away if things are overloaded, might be the way to do it. And so that's just a conjecture there, but one approach for that problem. All right, and so now we're going to move on to statistics. So in React, we use Folsom. And then now we use Xmeter, which I think still uses Folsom to some extent. There's some weird mix of things there. And these are mostly pure Erlang stats collection systems. So we're a database that likes to collect stats. Metrics are useful, right? And you want to know everything. And we collect lots of high, expensive stats, latencies. We collect histograms for everything, because just knowing counts is no fun. We want to know what your 99th percentile is, your 50th percentile, all that. But that's kind of expensive. In fact, it's been a huge problem in general for React over years of rewriting the stats system at different times. So the challenge here is we want to do simple stuff. Min and max is pretty easy. Mean's pretty easy. Counts are fairly easy. The hard stuff's actually just latency percentiles. That's actually kind of hard. And then there's just the reality here that we just keep adding new stats. Like every new major release of React, if you go back and look at it, like when we had to update the documentation, we're like, oh, we added 50 new stats this release or something. It's like something crazy like that. Because it's good to have the visibility when you're supporting a product, but these aren't free. There's work that has to be done to keep track of all this data. And so this has been an issue for React for years. We fixed counters. Counters used to be really slow. It used to be a single ETS increment atomic per metric. And of course, we're keeping like 100 counters. And so that still was a problem, even with individual counters per metric. We optimized this in React 1.3 as the way most people who optimize counters would, which is we have schedule partition counters and ETS. So we basically have the counter metric name underscore a scheduler ID. So if you have 8 scheduler threads, there's 8 counters. And then each thread checks the schedule ID, increments appropriate counter for that. And then when we update the actual counter, we aggregate those ones. That works out very well and has been great. Histograms, though, are still a challenge. They're the problem because you can't really partition them as easily. And they also have this crazy state space because we use reservoir sampling. And reservoir sampling is, you fill up a reservoir of data, and then once it's full, you then, every time you add new data, you randomly throw away a data up to a certain size within that window. And that's challenging to do that because you need to know your size. You need to consistently be able to update it to figure out the exact way. You can play games with it, but if you play games with it, you actually lose some of your statistical correctness. So we try not to do that. So let's write a NIF. So you can use min and max via atomics. There's an atomic max. You can also do an atomic min, but it's basically a while around an exchange. And we still do normal reservoir sampling. So these are non-partitioned, still shared central reservoir sampling. The difference here is it's in C, and we can use a single atomic increment to figure out where you are. That's really the only thing that's actually shared is the increment. Everyone needs to have the correct increment, and everyone then has from that be able to figure out how they can, which thing to discard. But then having concurrency of who discards what first and all that in the reservoir does not matter. That doesn't change the statistical sampling properties whatsoever. And so the only thing you actually need any consensus around is just that the counter. And so the atomic increment is fairly efficient, at least on x86 machines, which have an atomic increment internally. Might not be worth anything on ARM or something that doesn't, but at least for this, if we were to go and run this, I can't compare to React directly because this is in a different form. It's like stats as fast as possible, 1 second stats, whereas React does like 60-second stats. But I can tell you what a micro benchmark of this does. So a micro benchmark that does 200 metrics, where each metric is doing 10,000 updates per metric, or 10 million, sorry. And you have anywhere between 8 to 16 workers doing all this work, so lots of concurrency. It takes about 40 seconds to run, which, okay, that seems kind of long, but that's 50 million events per second. That's pretty good. I don't think React does 50 million stat updates per second. I think it probably does like 20,000. We'd have to see and compare this, but this is something that I definitely want to try to get integrated and compare to what we use internally for this system. And so the future of this is we could partition the reservoir sampler. There are ways to actually do partition reservoir sampling where you do it in a fancy way that you guarantee your statistical properties. There's a blog post from 2007 by this guy who works at Google who talks about that. It's something I've always wanted to try but haven't got around to doing. And then other than that, I'm basically done. NIFs can help us for certain things. I think we need to think about, though, how can we build cool reusable components in black boxes rather than like what a lot of people do eventually where they just abandon Erlang and rewrite their entire application in C or something. Let's preempt that by just fixing the things that are pain points. So yeah, reusable components. NIFs are kind of hard, though, because we have to deal with things like garbage collection, safe memory reclamation, allocation, copying, things that Erlang already does for us for free. We got to now figure out ourselves. So maybe we either taking the ideas that are already in Erlang and actually adding them to the NIF API, where you could actually perhaps use some of those features would be kind of neat, like the Erlang allocators you can't really use from NIFs. I mean, I guess you kind of can if you know the right internal thing to cast and use, but it's not part of the blessed API. There's just the standard enif allocate. And things like safe memory reclamation, what should we do there? What's the work in that space to do? And Erlang plus NIFs are even harder with like the garbage collection problem I talked about earlier, where something that should just be thrown away immediately. And like on the C version of that I tested originally, which is just using RAII, so the second you unwind the stack, it's free. Erlang is keeping 200 of these snapshots around now, which is blowing up our snapshot scans. That's no fun. But if we, I think it's worth it. It's worth it. Yeah, typo there. But there's more to do. And I have not yet pushed anything out there yet, and I don't know what it's going to be called or where it's going to live. It'll probably eventually live under Basho, but this will be a stable pointer that points to wherever it will be at some point when this code gets out next week or so. So my gtuple/ef 2015, and that's it.
Thanks for the talk. It's very interesting. Have you guys researched any potential memory fragmentations while using any of those data structures and those approaches?
I have not looked at memory fragmentation in this work directly, no. Not at all.
I guess it's just interesting because apparently ETS in some cases can actually cause very serious memory fragmentation. And memory doesn't really get reclaimed back by the VM. And because of that, it's actually interesting to kind of figure out how your memory usage changes when you use different data structures like that.
Yeah.
So if you do any research like that, please just post it somewhere because that would be awesome. Thanks.
Good point.
More questions for Joe Blomstedt?
Yeah, and they're making you walk, Nathan. Oh, and the next one's in the front.
Yes. Just interested in your reservoir sampling. What kind of, what is your percentage sampling that you do? Do you do 10%, 20%, 50%?
Sorry, what was that?
The reservoir sampling algorithm that you use for your histograms?
The reservoir sampling?
What about it?
What percentage of sampling do you do on your, for generating the histograms of your data? Like what
percentage are you allowing to be considered a sample and toss away?
So if you have 100
Yeah.
size of your
Uh-huh.
data is 100, what percentage of that is sampled?
Oh yeah, actually I don't know off the top of my head what it is. I just copied what we had in React and don't remember what it was, but that's some implementation we had before. I can look it up. I can look it up offline and talk to you.
Okay.
That's fine.
So earlier today, Larson gave a talk about two timers that's coming, and he said that there is no benefit to pinning this concurrent ETS updates, for example, or to specific threads, scheduler threads, schedulers.
Sure.
You just need to have enough of them.
Yep.
And have you tested those two modes when you do pinning and when you?
So we actually never really did direct pinning, right? I mean, we mostly used the schedule ID as just a uniform distribution function, right? I mean, it was just I wanted to have partitioned updates, which does help. That absolutely is a massive win. But it doesn't really need to have anything to do with the schedulers. Schedulers was an easy way to map concurrency to unique updates. It turned out there actually isn't the best approach, which is why the dispatch one's slightly better than SideJob. There are cases when Erlang decides to do thread compaction, right? I mean, it's actually one of the more useful things about the scheduler sometimes. Thread compaction is usually a good thing, so you have fewer run queues running, schedulers running your code. The problem is there are cases where you might get down only like 2 schedulers running your code. And so now if you're using your schedule ID as your metric to where you hash into this range, you actually have a much smaller set of updates now. And even though you have a bunch of different processes. So it's weird because there's an interesting trade-off. It's like, well, okay, I don't have the concurrency anymore. So the concurrency problem isn't there. Two workers is no big deal. I don't need to partition for concurrency reasons. But the problem is in that approach, the partitioning also determines how you're partitioning to the actual workers, like the run queue, the message queues. And so while concurrency isn't a problem anymore, contention's not a problem, you are now not really doing any kind of like uniform distribution of your work. You're spending most of your time sending your updates to one guy, and so his message queue gets really large, and you now have a bottleneck, one person doing that. And so actually I think scheduler threads are probably not the right way to do that for the mapping. Now for actually pinning things to particular threads, we've done some work before with that, but not in the context of this, and I can't really speak to that. But I know we've done stuff like pinning all of React's vnodes, specific CPU cores, and seeing how that would happen, things like that. And it's interesting because it doesn't help. Sometimes it does, sometimes it doesn't. You have to like get it just right. And that might be great if you're the person running a system like that in-house. But like for us, who we sell it to other people who run it, we'd have to configure every single cluster in the world to be just right for how we pin stuff, and that's a challenge. So.
Actually, I meant mapping, not pinning.
Yeah. Oh, the mapping. Yeah. Yeah, so the mapping is actually bad for not for the concurrency reasons, but bad just because it also it determines the distribution of your data, and that's actually a problem. It's something we want to fix. Yeah.
Question, fragmentation.
You had mentioned shared pointers. Did you ever see Herb Sutter's talk from CPPCon 2014 on using atomic shared pointers to do the sort of thing that you ended up using epochs for?
Yeah, you can use atomic shared pointers. They still have the same problem. The issue though is not the shared pointer itself. The issue is just that there's so many of them. You'd have a shared pointer for every allocation you have. And so if you have a deep tree, with epoch reclamation, the only thing I need to copy is the root node and its epoch, and I'm done. I don't actually have to go and increment all of the reference counts for every allocation that falls under all the paths of that tree, which is how you traditionally would do it. And so that's the main challenge. But yes, you need atomic shared pointers, period, to even do it in the first place. And that's actually a challenge, because atomic shared pointers are actually not supported in every platform right now either, because it either needs a lock or a double word compare and swap or other stuff in certain corner cases. Like there's these weird things about how it works. So try and like run atomic shared pointers on a Mac that's not like 1010 is very hard, for example. Can't get C-Lang to compile that way. But yeah, it's an interesting approach.
All right, one last question. Anybody? Fine, I will ask the last question.
Was it came in R16, they added the capacity to bump reduction counts in the NIF, the boundary.
Yeah, I need to do some of that. I need to play with that.
So that's my question, was if there's been any attempt.
I mean, we have years and years and years of playing with the schedulers properly, doing reduction count, all that normal NIF black magic sorcery that you do. So that's kind of old hat. I mean, we could do it. We need to. This, I was much more interested in, at least in this work, at this point of doing this new stuff. Like, how do you remember reclamation efficiently? How do you make it work with a garbage collector? That's stuff that's new that I don't have experience with yet. But yeah, reduction counts and things like that are useful. Turns out I don't know if that's a big problem though in these benchmarks because these NIFs are fast. Like, you know, I said before I have the spin weights on the flat combining, but then if it goes after a certain period of time, it switches to a message where it sends a message. It's never triggered the fallback unless in a test case where I make it have to trigger that because it just, you know, you're going and you're copying a pointer and you're updating a few things and you're done. So you probably would need a system with a lot more concurrency than I've tested on to have that problem.
All right. Another round of applause for Joe Blomstedt.